In this elementary algebra review tape, we're going to be going over our work on solving quadratic equations. We'll be solving quadratic equations by factoring, extracting roots, completing the squares, and finally by the quadratic formula. For our first example, let me break this into two parts. Let's first work out x squared minus 3x equals 0. This is actually the simplest type of quadratic equation to solve because the factoring is fairly obvious. We can pull out a common factor, x, times x minus 3 equals 0. Now, the whole principle of solving quadratic equations by factoring is that if you have, say, two real numbers, r and s, such that r times s equals 0, then either r equals 0 or s equals 0 or both. If r times s equals 0, if the product of two numbers is 0, ask yourself what that means. That means either the first number is 0 or the second number is 0 or both. And it's only with 0 that you can do that. For example, if I had the product of two numbers is equal to 12, I really don't have any definitive information about the numbers. Maybe one is 4, maybe one is 3, maybe one is 6, maybe one is 2. I don't know for sure anything. But if the product of two numbers is 0, then for sure either r equals 0, the first one is 0, or the second one is 0, possibly both is 0. Okay, so that's the whole beauty of having the 0 over here. And here we have our r times s equals 0. So then either x equals 0 or x minus 3 equals 0, giving us two roots, two solutions for this quadratic equation, x equals 0 and x equals 3. We add 3 to both sides, and we get x equals 3. Okay, and of course you can check your answers in the original equation. Now, what if we had, instead of x squared minus 3x equals 0, x squared minus 3x equals 10? This could still be done by factoring, but before we factor, we don't factor in this form. We don't say x times x minus 3 equals 10. There's nothing special about 10. It was 0 that had that special property. So what we have to do is first subtract 10 from both sides of the equation. Now we have 0 on the right-hand side. Now we look to put it in the form r times s equals 0. So we're looking for two numbers which multiply to minus 10 and add to minus 3, and they are minus 5 and plus 2. Checking, x squared plus 2x minus 5x gives us minus 3x minus 10. So now we have it in the form r times s equals 0, so we have either r equals 0 or s equals 0, both. And we solve, we get x equals 5 as one solution, x equals minus 2 as the other. And both of these can be checked in the original equation. You substitute x equals 5 in here, you get 25 minus 15, which is 10. You substitute in x equals minus 2, you get minus 2 squared, that's 4. Minus 3 times minus 2 is plus 6. 4 plus 6 equals 10. So they both check out. Okay, continuing. Let's try to solve this quadratic equation for x. X plus 5 times x plus 4 equals 12. Okay, now some people jump to the conclusion that, oh boy, here I'm getting it factored, I don't have to do any work. That's not true. It would only be beneficial to you if you had it factored with the right-hand side equal to 0. You can't really make use of it in this form. What you have to do is first multiply it out, set it equal to 12, subtract 12 from both sides, then refactor the resulting trinomial. So let's do that. You can't say, in other words, x plus 5 equals 12, x plus 4 equals 12. 12 is not 0. If the product of two numbers is 12, that does not mean that this number is 12 and this number is 12. The product of two numbers is 0. Then it means that this is 0 or that is 0. So you can't do anything with the 12. The only thing you can do here is to multiply it out. X squared plus 4x plus 5x, that gives you plus 9x plus 20 equals 12. Now subtracting 12 from both sides. X squared plus 9x plus 8 equals 0. And now that we have 0 on the right-hand side, we will try to factor the left. And it factors very nicely into x plus 8 times x plus 1. Two numbers which multiply to 8 and add to 9. X squared plus 9x plus 8. You set, therefore, the first number equal to 0 and the second one, giving us two solutions, x equals minus 8 and x equals minus 1. And of course, you can check these in the original equation. Checking minus 8 plus 5, that's minus 3. Minus 8 plus 4 is minus 4. Minus 3 times minus 4 does give you plus 12. And working with minus 1 plus 5, that's 4. Minus 1 plus 4, that's 3. 4 times 3 also gives you 12. So they both check out. Now let's look at the following fractional equation. 12 over x plus 1 minus 3 over x equals 2. And we know the way to solve a fractional equation is to multiply both sides of the equation by the LCD, the lowest common denominator, in an effort to remove fractions from the equation. And when we do that, in this particular example, a quadratic equation arises, which we will solve by factoring. Now, the LCD in this problem happens to be the product of the denominators x times x plus 1. So we will multiply both sides of the equation by x times x plus 1. And this means multiplying each and every term. OK, so x times x plus 1 times 12 over x plus 1 minus, don't forget the minus sign, x times x plus 1 times 3 over x equals x times x plus 1 times 2. Each part of the equation, both sides of the equation were multiplied by x times x plus 1, and on the left that meant distributing it. Okay, so x times x plus 1 times this minus x times x plus 1 times that equals x times x plus 1 times that. Now, what happens over here? The x plus 1's cancel, leaving you with 12x minus, here the x's cancel, leaving you with 3 times x plus 1. And here, nothing cancels. We just get 2x times x plus 1. Now distribute the minus 3 through the parentheses, giving you minus 3x minus 3 equals, here distribute the 2x through the parentheses, giving you 2x squared plus 2x. Now, let's see what we have. On the left, 12x minus 3x. That gives you 9x minus 3 equals 2x squared plus 2x. Now we can subtract 9x from both sides of the equation. We'd like to get everything on one side equal to 0. That's the way we solve quadratic equations. So this gives us minus 3 equals 2x squared minus 7x. And finally, we're going to add 3 to both sides of the equation. Let's see what we had. We had minus 3 equals 2x squared minus 7x, adding 3 to both sides. 0 equals 2x squared minus 7x plus 3. We're now in an ideal form. We would like to factor the right-hand side, in this case, and we'd have the product of two numbers equal to 0. And this factors you know it has to have the 2x and the x there, and 2x minus 1, x minus 3 works. 2x squared minus 6x minus 1x, that's minus 7x plus 3. The factoring here is not as obvious as in the preceding examples. Here you'd actually have to figure out, should the 3 go here or the 1, vice versa. Okay, product of two numbers equals 0. That means either 2x minus 1 equals 0 or x minus 3 equals 0, giving us here x equals 3 as a solution. Here, adding 1, 2x equals 1, then dividing by 2, x equals 1/2. And we know that any equation we would like to check, but it's particularly important in a fractional equation that contains variables in the denominator. 12 over x plus 1 minus 3 over x equals 2. It's the original equation we go back to. Let us check x equals 1/2, and then we'll check the x equals 3. If x equals 1/2, we get 12 over 1/2 plus 1 minus 3 over 1/2 should be equal to 2. 12 over 1/2 plus 1, that's 1/2 plus 2/2, that's 3/2, minus 3 over 1/2 should be equal to 2. And instead of dividing by fractions, of course, we can invert and multiply, giving us 12 times 2/3 minus 3 times 2 over 1 should be equal to 2. Well, 3 goes into 12 4 times. 8 minus 6 should be equal to 2, and that checks out. Going over this again, we have 4 times 2, 8 minus 6, which should be equal to 2, and that checks out. Now, checking x equals 3. 12 over 3 plus 1 minus 3 over 3 should be equal to 2. 12 over 4 minus 3 over 3 should be equal to 2. And 12 over 4, that's 3 minus 1, which of course equals 2. Checks out. Now we have seen several examples in which we solved quadratic equations by factoring. Let's look at another example here. We want to solve for x. X squared equals 16. Now this could also be solved by factoring. We could subtract 16 from both sides of the equation, factors easily into x plus 4 times x minus 4, and set each factor equal to 0, giving us x equals minus 4 and x equals plus 4 as two solutions. In this particular problem, however, there happens to be another, in fact, easier way to go about solving this problem. What makes this problem special is that the left side is a perfect square. Okay, in this particular case, there is no first-degree term, like 2x, 3x, something like that. If the left side is a perfect square, what we can do is take square roots of both sides. Let's look at another way of solving this equation. X squared equals 16. We take square roots of both sides. X is plus or minus the square root of 16. X is plus or minus 4 automatically. Okay, so here is the same result with much less work. And the whole idea when you're working with extracting roots is to get the left side to be a perfect square. Let's look at, or to try to see that it's a perfect square. If we have, for example, this problem, solve for x. 3x squared equals 18. The first thing I would do would be to divide both sides by 3. Then you'd have x squared equals 6. And then you could solve this by extracting roots. X is plus or minus the square root of 6. Remember, I said the left side should be a perfect square, nothing about the right side having to be a perfect square. If it is, like over here, well, then your final answer does not involve a radical. Plus or minus the square root of 16, so you get plus or minus 4. But if the right side is not a perfect square, well, then your answer will involve a radical, but it's still the answer. You get x equals plus the square root of 6, x equals minus the square root of 6 as two possible answers. In the next example, solve for x. And the left side is given as x minus 5 squared equals 7. So it's clear that the left side is a perfect square. We'll solve this by extracting roots. X minus 5 is plus or minus the square root of 7. Adding 5 to both sides, it's a little different from the other problems in that the other problems all had x squared. Here we have something else squared. But still, when we take square roots, we get x minus 5 is plus or minus the square root of 7. And that gives us x minus 5 is equal to plus the square root of 7, or x minus 5 is minus the square root of 7. And adding 5, we get 5 plus the square root of 7 and 5 minus the square root of 7 as our two solutions. Of course, we could have added the 5 here, 5 plus or minus the square root of 7. But remember, that's two solutions, 5 plus the square root of 7 and 5 minus the square root of 7. Now, as I mentioned, the technique of extracting roots can only be used if the left-hand side is a perfect square. What if the left-hand side is not a perfect square? For example, x squared minus 8x plus 5 equals 0. All right. This particular problem cannot be solved by factoring. Methods that we used earlier, we cannot factor it into two binomials with integer coefficients. Okay, so what we'd like to do is see if there's somehow a way of, so to speak, completing the square so that the left side would be a perfect square. In fact, that's what I want you to do here, solve by completing the square. It really means solve by extracting roots, assuming you had a perfect square on the left-hand side. And since you don't, you first have to get that perfect square on the left-hand side. OK, and what we do is we subtract the constant from both sides of the equation. This is a little contrary to what we usually do with quadratic equations. We don't leave the 0 here. In fact, what we do here is to subtract 5 from both sides, and we have this. Now, we try to figure out what perfect square would x squared minus 8x come from. And we use as our model the following. We know that x plus p squared, which is x plus p times x plus p, using FOIL. This is x squared plus px, that's plus 2px, plus the last p squared. And we try to match what we have to this. That is, we have x squared minus 8x. We think of the coefficient here as the 2p. And we know that if we could add p squared, that would make it a perfect square. So we say to ourselves, well, 2p is minus 8. P is therefore minus 4. P squared that we are looking for, what we're missing to have a perfect square, is 16. That is, if this were x squared minus 8x plus 16, then this would be a perfect square, namely x minus 4 squared. This can be checked. It's x squared minus 8x plus 16. So we had just this, and the question is, what is it missing to be a perfect square? And the trick is to take the coefficient of x, halve it, gives us minus 4, square that, and that's what it's missing to be a perfect square. And you can actually write it down mechanically. 2p is minus 8. Halve it to find p. Square it to get p squared. In any event, we know that what we need to do is we could add 16 here, we'd have a perfect square. But it's an equation, so of course we have to add 16 to both sides of the equation. On the right-hand side, minus 5 plus 16 is 11. On the left-hand side, we have x squared minus 8x plus 16, but that's precisely x minus 4 squared. In other words, we now have this problem looking like the preceding problem, which we solved by extracting roots, because the left-hand side is a perfect square. Remember the preceding problem? Let's go back over here for a second. The last problem we had x minus 5 squared equals 7. It was given to us in that form. Well, then x minus 5 is plus or minus the square root of 7, and we continued on down. The left side was given as a perfect square. Here we had to do some work, but the end result is now the left side is a perfect square. So x minus 4 is plus or minus the square root of 11. And adding 4 to both sides, x is 4 plus or minus the square root of 11. So there are two roots. Two solutions here. 4 plus the square root of 11 and 4 minus the square root of 11. Okay, now don't let the fact that there are radicals here upset you. You can still check your answers in the original equation. Okay, it can be done. It would not be terribly difficult. You would take 4 plus the square root of 11, square it, subtract off 8 times that, add 5. The square roots of 11 would drop out, and it would work out. Okay, so each of these could be checked in the original equation. Okay, let's try another example. Solve by completing the square. (4x squared plus 24x minus 3 equals 0). Okay, this particular problem cannot be solved by factoring. We're going to do it by completing the square. The same way that we did last time, we're going to first add the constant, get the constant over to the other side. In this case, we add 3 to both sides, giving us this. There is a slight difference between this and the preceding problem in that the coefficient of x squared is not 1, it's 4. And the model that I gave you before, x plus p squared, is x squared plus 2px plus p squared, was based on having the coefficient of x 1. You could make up a new model, but why learn a new model when it's simple enough to get this in that form? All we're going to do is divide both sides of the equation by 4 so that this will be a 1x squared. Okay, so let's divide by 4. Means every term gets divided by 4. 4x squared over 4, 24x, so 4 equals 3 over 4. This gives us x squared plus 6x equals 3/4. And we want to add some quantity here so that this will be a perfect square. Going back over here, we have x squared plus 6x. We want to add p squared. That'll make it a perfect square. If you think of 2p as 6, halving that gives you p equals 3, p squared equals 9. But if you were to add 9, this would be a perfect square, namely x plus p, or x plus 3 squared. Okay, so that's what has to be added to both sides here to get us a perfect square. Okay, and this can be done in your head. You simply take the coefficient, halve it, get 3, square it, it's 9, and that's what you add to both sides. The left side is x squared plus 6x plus 9, or x plus 3 squared. It's a perfect square. The right side is 3/4 plus 9. Well, 9 can be thought of as 36/4. 36/4 plus 3/4, that's 39/4. We have x plus 3 squared equals 39/4. And now we can solve this by extracting roots because the left-hand side is a perfect square. X plus 3 equals plus or minus the square root of 39/4. X plus 3 is plus or minus. Now we have a fraction under a radical sign. To put this in simplest radical form, we would say it's the square root of 39 over the square root of 4, which is 2. The square root of 39 over the square root of 4. Now it's in simplest radical form. We then subtract 3 from both sides of the equation. X equals minus 3 plus or minus the square root of 39 over 2. Minus 3 plus the square root of 39 over 2, and minus 3 minus the square root of 39 over 2. Two solutions. Okay. The final method for solving quadratic equations is to use the quadratic formula, and it can be used on any example. The ones that you can do by factoring can also be done by the formula. The ones you can do by extracting the roots or completing the square. However, if you can do a problem by factoring, it's generally the easiest way to go. The formula, while it always works, can be a little more tedious. Okay, but let's just go over the idea. We want to solve for x. The following equation, x squared minus 3x minus 5 equals 0. This particular problem we couldn't solve by factoring anyway. Make it a little neater. Quadratic formula says if you have a quadratic equation of the form ax squared plus bx plus c equals 0, the roots of this particular equation are given by the following formula. The formula, by the way, is derived by doing the procedure we did on the last problem, but on the general equation rather than on a specific example, where it's subtracting the c from both sides, dividing through by the a, completing the square, and extracting the roots. But if you do it once and for all on this particular general equation, then you will have the formula, and you can always use it. The formula gives you x equals minus b plus or minus the square root of b squared minus 4ac over 2a. We're assuming, of course, that a is not 0, or else it wouldn't be a quadratic equation, just be a first-degree equation. Okay, the first thing to do is to figure out what a, b, and c are, okay, and actually write them down. A is the coefficient of x squared, so a is 1 here. B is the coefficient of x, it's minus 3, and c is the constant term, it is minus 5. So x equals minus b. And actually make the substitution, directly. Don't simplify on this level. Minus b. B is minus 3. Plus or minus the square root of b squared, that's minus 3 squared. Minus 4ac. Minus 4 times a, which is 1, times c, which is minus 5, all over 2a. Now, minus a minus 3, that's plus 3. Plus or minus the square root of. Minus 3 squared, that is 9. Minus 4 times minus 5, that's plus 20. So 9 plus 20, that's 29 under the radical over 2. So 3 plus or minus the square root of 29 over 2. Just one word of caution. When you do a problem by the quadratic formula, everything is over 2a. It's this whole thing over 2a, or the whole thing in this case over 2. Whereas when you do a problem by completing the square and extracting roots, okay, you very often get just something plus or minus. Now this was the only part that was over 2. Okay, but in the quadratic equation, it's the entire numerator over 2a. Everything up there over 2a. Okay, for a last example, let's do one more problem by the quadratic formula. Problem 10, solve for x 3x squared plus 4x plus 2 is x squared minus 2x minus 1. Okay, now I haven't told you how to do this problem. I did say we're going to do it by the formula. Don't do a problem by completing the square unless it's, it says explicitly solve by completing the square. Generally, if you can factor or extract the roots directly, that's going to be easier than the quadratic formula. But the quadratic formula, which has been derived from completing the square, is usually easier than completing the square. So don't do the completing the square unless the problem specifically calls for it. All right, now first we'll have to simplify this example. Let's see what we can do here. We can subtract x squared from both sides of the equation, giving us 2x squared plus 4x plus 2 equals minus 2x minus 1. Then we can add 2x to both sides. 2x squared plus 6x plus 2 equals minus 1. And finally, add 1 to both sides. 2x squared plus 6x plus 3 equals 0. And we're going to match this up to ax squared plus bx plus c equals 0. And we see that a is equal to 2, b equals 6, c equals 3. Let's write that down. A equals 2, b equals 6, c equals 3. We will now solve by the quadratic formula. X is minus b plus or minus the square root of b squared minus 4ac all over 2a. That is minus 6 plus or minus the square root b squared, 6 squared, minus 4 times a, which is 2, times c, which is 3, all over 2a, or 2 times 2. What do we have? X equals minus 6 plus or minus the square root of 36 minus 4 times 2, that's 8, times 3, that's 24. All over 2 times 2, or 4. X is minus 6 plus or minus the square root of 12 over 4. Now, as always, we'd like to express our answers in simplest radical form, and the square root of 12 can be simplified. We can write it as the square root of 4 times 3, a perfect square times whatever's left over. And the square root of 4 times 3 is the square root of 4 times the square root of 3, or 2 times the square root of 3. So we get x is minus 6 plus or minus the square root of 4, which is 2, times the square root of 3, all over 4. And we can now simplify a little more because there are factors in common in the numerator and the denominator. Now, don't get sloppy and, for example, figure you can cancel the 2 into the 4. You have to look at the entire numerator and see if there's anything. Right now, we have a sum or difference of terms. We have to see if there's any common factors. We can pull a 2 out, but from both terms, leaving you with minus 3 plus or minus the square root of 3 over 4, which is 2 times 2. Now that you've factored, you can cancel these 2's, giving you a final answer of minus 3 plus or minus the square root of 3 all over 2. And that brings us to the end of this tape.